Ever wondered how your computer's brain really works? Let's dive into CPU and memory basics. Your CPU is the powerhouse, executing instructions lightning fast. But without enough memory, it's like a chef without ingredients, a bottleneck to speed. In real programs, performance is key. Picture your CPU as the conductor of an orchestra, directing each player, memory, storage, for flawless harmony. To unleash your computer's full potential, understanding this dynamic duo is crucial. Stay tuned to unravel the secrets behind your computer's brainpower. Welcome to our course overview. Today, we embark on a journey delving into the intricate world of computer architecture. Our first stop, CPU pipeline mechanics. Witness how processors execute multiple instructions simultaneously, unlocking unprecedented speed. Next, we uncover the magic of cache memory systems, the unsung hero behind lightning-fast program execution. Moving along, we unravel the mysteries of RAM and memory hierarchy, striking a balance between speed and capacity. Then, we dive into the heart of computation with the instruction execution cycle, the engine powering all tasks. Lastly, we bridge hardware insights with software finesse and performance optimization, crafting code that's both swift and efficient. Ready to unlock the secrets of computing prowess? Let's begin. Ever wondered how your computer processes tasks at lightning speed? Meet the CPU, the powerhouse behind it all. This tiny but mighty component tackles billions of instructions per second, thanks to a smart strategy called pipelining. Picture a busy factory assembly line, where each worker handles a different task concurrently. Similarly, the CPU breaks down your program's commands into stages that can overlap, boosting efficiency. It's like a well-oiled machine, smoothly juggling multiple tasks at once. So, next time you click or type, remember it's the CPU orchestrating this high-speed symphony. Imagine a world where a processor must painstakingly complete each instruction before moving on to the next. Picture this: fetching, decoding, executing, and then finally completing each step, all taking a whole 5 nanoseconds for just one instruction. And then, another 5 nanoseconds of waiting. And still, the cycle continues. This sequential approach wastes precious time, leaving CPU hardware idle and unutilized. But fear not, for we can revolutionize this process and do so much better. Let's dive into the world of pipelining and witness the incredible efficiency it brings to computing. Ever wonder how modern CPUs achieve lightning-fast speeds? It's all about parallel instruction processing through the CPU pipeline. Picture this: while one instruction is being decoded, another is being fetched, and a third is executing simultaneously. This clever strategy results in a remarkable 5x speedup compared to sequential processing. Despite each stage taking just 1 nanosecond, multiple instructions are in flight at once. The payoff? Once the initial startup delay is overcome, the CPU churns out roughly 1 instruction per nanosecond, enabling billions of instructions per second. In essence, it's like a well-coordinated orchestra where every section plays its part, resulting in a symphony of computational prowess. Ever wonder how a computer processes instructions so quickly? Enter the 5 classic pipeline stages. First up, fetch, grabbing the next instruction from memory. Then comes decode, where the operation is identified. Next is execute, where the magic happens. Memory is all about data access, and write back stores the result. Each stage works on a different instruction simultaneously, creating a powerful overlapping effect. This efficient process is what makes pipelining so effective in computing. Ever wondered how pipelines boost performance in computing? Let's dive into an eye-opening example. In a sequential execution scenario, 3 instructions traverse 5 stages, taking a total of 15 nanoseconds. That averages out to 5 nanoseconds per instruction. Now, shifting to pipelined execution with the same setup, but with instructions overlapping in the pipeline, the total time reduces to just 7 nanoseconds, averaging around 1.7 nanoseconds per instruction. The key insight here is that once the pipeline fills up, we're able to complete 1 instruction per clock cycle, showcasing how CPU clock speed directly impacts instructions per second. In essence, pipelines streamline processes, significantly enhancing efficiency. Ever wondered why modern computers face a memory hierarchy challenge? Picture this: CPUs blazingly fast, executing instructions in a nanosecond, while fetching data from RAM takes 50 to 100 nanoseconds, a 100x speed gap. Without a solution, CPUs would be idle 99% of the time. The remedy? Introduce a tiered memory system with cache memory bridging the gap. Think of it as creating a speed expressway between the CPU and RAM. This hierarchy of memory levels ensures the CPU always has quick access to the data it needs. So, the next time you marvel at your computer's speed, remember the intricate dance of memory hierarchy at play. Ever wondered how computers manage to balance speed and storage capacity in their memory systems? At the top of the hierarchy are the lightning-fast CPU registers, with a mere kilobyte of space but near instantaneous access. Moving down, we encounter the L1, L2, and L3 caches, each offering more storage but slightly slower retrieval times. Main memory, or RAM, provides a significant leap in capacity, albeit with a trade-off in speed. The key to optimal performance lies in strategically storing frequently accessed data closer to the CPU, navigating this delicate balance between speed and capacity. As we delve deeper into the memory pyramid, the need for efficient data management becomes increasingly apparent. In this intricate dance between speed and storage, the essence of performance optimization emerges, keeping vital data within reach of the processor while leveraging the varying capacities of each memory tier. What exactly is cache memory? Imagine a tiny, lightning-fast memory sitting right next to the CPU, storing frequently accessed data from main memory. When the CPU needs info, it checks the cache first, finds it there, quick, or fetches from slower RAM if it misses. With multiple levels like L1, L2, and L3, cache sizes grow but get slightly slower. L1 can be accessed in just 1 nanosecond, nearly as fast as the CPU itself. This staggering speed difference is key for top performance. Cache offers a whopping 100x speed advantage over RAM access time, with a typical hit rate of 95% for well-optimized programs. Think about that. Ever wonder why cache memory is so effective? It all comes down to the principle of locality, the key to optimizing code for speed. First up, we have temporal locality, which suggests that if you use a variable now, you'll likely use it again soon. Think of loop counters or frequently called functions. Caching recent data taps into this pattern. On the other hand, spatial locality predicts that if you access one memory address, you'll soon access nearby ones. This is crucial for array processing and sequential instruction execution. Caches leverage this by fetching blocks of adjacent memory. By understanding and harnessing these principles, you can write code that performs at its best. Remember, when it comes to optimizing performance, locality is key. Ever wondered how memory access patterns can impact performance in computing? Let's delve into cache performance with a real example. Picture summing a 2D array. One method goes row by row, while the other jumps column by column. Same task, but vastly different outcomes. In the good scenario, we loop through elements sequentially, achieving a 95% cache hit rate. This means efficient memory usage, minimizing slow RAM access. Contrast this with the poor approach, where we jump across memory, yielding a meager 30% cache hit rate. The result? The good version runs a remarkable 3 to 5 times faster than the poor one, solely due to distinct memory access patterns. Remember, how you access memory can make or break your performance. Ever wondered where your computer's programs and data reside while in use? Enter Random Access Memory, or RAM, the bustling main memory of your system. Unlike cache, RAM boasts gigabytes of space to house your OS, apps, and files. Thanks to its random access nature, fetching data swiftly is its forte, even if it lags behind cache speeds. With a typical read time of 100 nanoseconds and capacities like 64 gigabytes in modern desktops, RAM ensures smooth data flow at 25 gigabytes per second. Remember, in the memory hierarchy, RAM plays a crucial role bridging the gap between high-speed cache and slower storage. Ever wonder how your computer swiftly retrieves data for your programs? Enter the memory hierarchy. Picture this: your CPU acts as the commander, swiftly fetching data from the L1 cache with lightning-fast 1 nanosecond latency. If not found, it delves into the L2 cache at 5 nanoseconds, then the shared L3 cache at 15 nanoseconds, before resorting to the slowest but largest RAM at 100 nanoseconds. The magic lies in the seamless, behind-the-scenes operation where each cache level automatically copies data. By grasping this hierarchy, you can optimize code to keep essential data in the fast cache, enhancing performance. Remember, the key to efficient programming lies in understanding the memory hierarchy. Ever wonder how your high-level code transforms into the lightning-fast actions of your computer? Welcome to Chapter 4, the Instruction Execution Cycle. Here, we dive into the heartbeat of computing, the relentless loop of fetching, decoding, and executing machine instructions. With each cycle occurring billions of times per second, modern processors are veritable speed demons. From Python to Java to C++, your code undergoes a remarkable metamorphosis, emerging as simple operations orchestrated by the hardware. Witness the magic as your digital commands come to life in a symphony of binary brilliance. Ever wonder how a computer knows what to do next? Enter the fetch decode execute cycle. The CPU swiftly retrieves instructions from memory using the program counter, decodes these commands, and executes them through the ALU. Each cycle seamlessly flows into the next, maximizing efficiency. Picture a well-oiled machine, tirelessly churning through tasks at lightning speed. This intricate dance of fetch, decode, and execute is the heartbeat of computing, driving our devices to perform with precision and speed. Ever wondered how a simple addition operation really unfolds in a computer's instruction cycle? Let's delve into the layers of complexity hidden beneath the surface. First, the values of A and B are fetched from memory and loaded into registers R1 and R2. Then, the ALU performs the addition operation, adding R1 and R2 and storing the result in R3. Finally, the result is written back to memory at the address of C. These seemingly straightforward steps actually involve a series of intricate machine instructions. By understanding this process, we see the importance of pipelining, allowing for overlapping execution and significantly reducing the overall clock cycles needed. In a world where efficiency is key, optimizing instruction execution can make all the difference. Ever wondered what really drives program performance? It all boils down to 3 key factors: the number of instructions your program requires, the speed at which the CPU can execute each instruction, and how often the CPU needs to wait for memory. The crème de la crème of programs excel by minimizing all 3. They use efficient algorithms, optimize data access patterns for cache hits, and strive to keep the pipeline flowing smoothly by reducing branching. By delving into the intricacies of hardware, you can craft software that operates exponentially faster. In the realm of performance optimization, success hinges on streamlining instruction sets, maximizing cache efficiency, and minimizing CPU idle time. This trifecta of strategies not only enhances program speed but also unlocks the full potential of your software. So, remember, efficiency in algorithms, precision in data access, and a streamlined pipeline pave the way for exceptional performance. Ever wondered what goes into the performance equation of a computer system? It's a delicate balance of instructions executed, cycles per instruction, and clock speed. Better algorithms mean fewer instructions, cache-friendly code reduces memory stalls, and faster CPUs boast higher clock speeds. A well-oiled pipeline keeps the cycles per instruction close to 1. Imagine a program with poor cache behavior. Half the time is spent waiting for memory. Now, picture an optimized program with good cache behavior. Only 5% of the time is wasted. Efficiency matters. In the world of computing, every factor plays a crucial role in maximizing performance. Ever wondered how modern CPUs execute instructions at lightning speed? It's all thanks to pipelining, allowing for parallelism and achieving around 1 instruction per clock cycle. And cache memory? It's a performance powerhouse, 100 times faster than RAM, boosting program speed by storing frequently accessed data. The memory hierarchy, from registers to RAM, balances speed and capacity, guiding optimal data access strategies. Simplifying every program into fetch decode execute cycles, high-level optimizations aim to minimize instructions and memory accesses. Remember, performance is a dance between hardware and software design. Sequential memory access, data reuse, and minimal branching are key. By mastering CPU and memory fundamentals, you'll shift from hoping your code runs fast to understanding how to make it faster.